Hi everyone, Chris Tisdale here again. Thanks for tuning in. In this presentation, I'm going to continue my series of videos on calculus, and in particular, I'm going to solve an example involving a power series. We're going to discuss how to find the interval of convergence and test the endpoints of the interval. So let me share my screen with you and we can get down to business. So the first thing you see is that this screen or the font is massive. It's because I'm trying to get better at being visible on mobile devices. So if you're watching on a mobile device, can you read the font okay? We're asked to determine the interval of convergence for this power series here. And I'll put the function here, just defining the function for a particular reason. So first of all, this is a special kind of series called a power series. It involves powers of x. And in particular, you can write this, if I can just squeeze it in, as something like akx to the k. All right? So a sub k here would be 1 on 3 to the k times k squared. Now, the reason that I've defined that function f of x there is because it kind of gives you a hint of what the question's actually asking. The question is actually asking you to calculate the domain of f. What values of x make f of x make sense? So let me show you. So when we're asked to determine the interval of convergence for this power series, imagine this is a function of x. We want to calculate the domain of this function. Okay, so how do we do it? Well, we use an idea called the ratio test. So we are going to look at the ratio of this whole thing with k replaced by k plus 1 over this thing. So let me show you here. Okay, so let me move that up a bit. So consider this ratio. We're going to apply an idea called the ratio test. Now, of course, these things cancel out straight away and you just get x here. But let's just write it in just for completeness. Okay, so we'll replace k with k plus 1 throughout. So I get x to the k plus 1. And on the bottom, I'll get 3 to the k plus 1 times k plus 1 all squared. And instead of sort of dividing again, I'll multiply through by the reciprocal. So let's just put this, flip it, and we'll multiply through. Okay, so you can see that, okay, yes, the x to the k's are going to cancel out. You'll be left with x. The 3 to the k's are going to cancel out. You'll be left with 3 on the bottom. And then you've got a k squared and a k plus 1 squared. So let's simplify this a little bit. So these things will cancel out, and I'll be left with this. I'll be left with a 3 on the bottom. And then I'm left with k squared over k plus 1 squared. So I can get rid of these absolute value signs because everything else is non-negative. So let's put this over 1, k1, sorry. Let's put this over 1 squared sign. Okay, so now what we're going to do is look at the limit of this as k goes to infinity. Okay, that's the usual standard process. So look at the limit of this as k goes to infinity and then find out what values of x will make this whole thing less than 1. All right, so what I'm going to do is I'm going to divide, to make the limit easy, I'm going to divide top and bottom in here by the highest power in the denominator. So it'll be 1 over 1 plus 1 on k inside. Yeah. And now you can see as k goes to infinity, this thing's going to go to 0 and I get 1 squared, which is just 1. So I end up with this. Now, the ratio test tells us that ratio, when that ratio is strictly less than 1, the series converges. So let's find all the x values that make absolute x on 3 strictly less than 1. Okay, so, well, bring that up there. So we've got absolute x less than 3, get rid of the absolute value signs, and we'll get the following. All right, so this is an important step now. This is the beginning of our interval. Okay, so let's make a conclusion here by ratio test, and let's call this star. Let's say, okay, star converges for x in this interval. Okay. Now we're not quite finished because we don't know what happens at the edge of this interval, right? What happens at the endpoints? So the final step in this solution method is to test the endpoints of the interval. Okay, so let's do that. Now for that you need to know how to deal with series of constants. Okay, so we've applied the ratio test. We know that the interval or the domain of this is at least this interval, but can it be a little bit wider? So that's what we're going to do in the next part. Okay, so here we're going to test. Basically, I'm going to put in the endpoints into f. So I'm going to replace x with 3 and x with -3 and see what happens. Does the thing make sense? Is it well defined? So if I replace x with 3, I'm going to get 3 to the k on 3 to the k. That'll cancel that, and I'll get the sum of 1 on k squared. So it's a sum of constants. Okay, so these things are going to cancel off, and I get 1 on k squared. Now, this is a special kind of series called a p-series. It's 1 on k to some power, and the power here is 2, which is greater than 1, so we know that this whole thing converges. Convergent p-series with p equal to 2, which is strictly greater than 1. Okay, so this is the test. If p was less than or equal to 1, this thing would diverge. Okay, let's test the other endpoint. We want to replace x with -3 in here, so I'm going to get -3 to the k. All right. All right. Now, I can take out a -1 to the k, and I'm left with -1 all to the k times 3 to the k. So that'll cancel out, similarly to up here, but you'll just be left with -1 to the k. And now the question is, does this series converge or diverge? Well, if you look at the absolute value of that, the top will just become 1, and you get the same series up here. So you can say since the absolute value, this series absolutely converges, there's a theorem that tells you the original series has to also converge. So we know that this series is a convergent p-series. That tells us that the original series, so let's call this, I don't know, double star. Okay, so what does this mean? Well, it means that f of 3 is well defined and f of negative 3 is well defined. Well, the series converges for x equals 3 and the series converges for x equals negative 3. So they're both in the domain of f. Let's write that down. So these things are well defined. All right, so let's take what we got on the other page. Here's our interval of convergence, and if we include the endpoints, x equals 3 and x equals negative 3, then we put them together and we get a big interval. So our conclusion then is the interval of convergence is, and just to make it clear, it's the domain of this function. Okay. Now, what would happen if this series converged and this series diverged? Well, we wouldn't include this endpoint, so you'd have sort of an open bracket here, and so on. What do you think? The idea is very similar for all the kinds of power series. Look at the ratio, take the limit, in this case with respect to k, as k goes to infinity, then find out what values of x make that strictly less than 1. Solve that for x, and you've got the start of your interval. Then, if needed, test the endpoints of the interval. Okay? Anyway, hope you enjoyed this presentation. If you have any comments, any questions, I'd love to hear them. You can put them in the comment section. And thanks for watching. See you. Bye.